Hello, class. We were able to introduce a little bit of linear transformations today in class. Now we're going to go over some things that might be a little bit more technical about what the exact definition is of a linear transformation, some language about the input space and the output space and stuff like that, and a few more examples. And we'll build up to the easy way, the straightforward way, a really slick way of figuring out what matrix does a certain transformation. So one way to think about matrix multiplication is that it transforms vectors. So it transforms one vector, you multiply it by, you get a new vector. You can think of it as stretching, squishing, rotating, reflecting one vector into another vector. So this transforming way, independent of the context, no matter what the units are here, we could end up with the same multiplication in different contexts, but if you take away the contexts, then there's still, like, you still start with this vector and you still end with this vector. So it makes sense to just start thinking about what's the process of going from that vector to this vector, and geometrically, is there a way to make sense of it that can help us understand more about linear algebra and matrix multiplication. So a transformation will take as an input a vector in Rn and map it to Rm. So in an n by n matrix, they're m by n matrices. M by n matrices. If there's n columns, this is the number of columns. That is your input space. So that's why it starts with Rn. Right? If I have if I've got this space like this, then I need to multiply that by a really long skinny matrix. I need 4 quantities over there to do this multiplication. So I'm starting in R4, but where am I going to end up? I've only got 2 rows. I'm going to end up in R2. So I'm going to go from R4 into R2. So that's where the n actually is where we're starting. The m is where the space where we're ending. Where we're starting, this is called the domain, and the space we go into is the codomain. The codomain sure does not like that. There, the codomain. So that's what these are, and the notation T is the name of the transformation, and it goes from Rn to Rm. Sometimes they'll say X maps or goes to, or goes to, or is sent to T of X. So, boy, I'm going to win the award for the worst handwriting on videos. For vector X in Rn, the vector T of X in R of M is called the image. So this is our output. Right? We're going to R of M. It's called the image. So X goes to a new vector, and that new vector is called the image. You can think about, I don't know a good way to think about it. And the set of all images T of X is called the range. So we might not fill the codomain. We might not get every single point in R2. We might just fill a subset. And so the range in the codomain might be different. And there's a nice image on this next piece. So here's the domain in Rn, and it'll map us to a codomain. So in this case, the codomain is R3. It looks like it's R3, but the range, we only fill out part of that, and the range is actually where we end up. That plane that we map to, it lives in R3, so the codomain's R3, but we only span 2 dimensions, and so the places we actually reach is called the range. So that's the difference between the range and the codomain. They could be the same, but they might not always be. the same. So what is the domain and codomain of T? So here is a matrix A. This matrix is going to do a transformation for all x in R2. So we start with an x in R2, right? This is the xy. We can do that multiplication. And what are we going to end up with? We're going to end up with something in a vector in R3. So the domain is all of R2. We can multiply by anything there. Do we get all of R3? It's impossible for us to get all of R3. We can't span all of R3. We only have two vectors here. So, and they're linearly independent. So we're going to the image will only be a two-dimensional plane, but it's going to live in the codomain of R3. So the image will be some two-dimensional plane in R3. The codomain's R3 because I'm going to get three values over here. So after I do that multiplication, those are supposed to be boxes, then I'm going to get, here, let's do it this way. X minus 2y, x plus y, 3x plus 7y. Those are going to be my three values in my new vector. So any xy, it goes to this set, but it lives in R3 because I have 3 coordinates. But I know I can't span all of R3. So the codomain is R3, but the image will be less than R3 because I only have 2 independent vectors. The most I can span is so I will span a 2-dimensional space. So let B and U be that. Compute T of U. So transforming U, I just have to multiply T times U. This A times U. So that's just a simple matrix multiplication. I'll let you do that. Is B in the range of T? If so, find a vector X where T of X equals B. So here we can do we can use our row reduction strategy and set this augmented matrix up, and that's finding our xy that we can multiply by A to get minus 1, 2, 10. So this already lives in our domain, U, so we just have to multiply to find out where it is in the codomain. This is in the codomain. We're not sure if it's in the range. We're not sure if we can actually get there with these combinations. This is how we test. So the range of T, that's going to be the span of these two things. And this is the way we worked out these last problems. This is someone else's work that has much neater handwriting than mine. So for the transformation, T of some linear transformation, that we can always take a linear transformation and write it as a matrix multiplication. We have these rows of the columns A multiplied by a vector. You get these x's become weights on the columns, and so B is in the range of T. So this is a B vector. It's in the range of T for some x if you can multiply A by x and get B, or if there's some coordinates of x1, x2, x3, etc., xn for the columns of A. So if you can have a linear combination of A, of the columns of A to get B, or if B is in the column space of A, all of those are the same thing. So the range of T of X is the column space of A. The transformation is linear if for all uv in the domain of T and all scalars C, these things are true. In class, we said the intuitive idea is it's linear because it takes lines to lines and the zero stays in the same spot. So lines to lines. But this is equivalent, and these are easier to do proofs with, so mathematicians like these. But the idea is if you have the sum of two vectors, then to find out how the sum of the vectors is transformed, you can just transform the first, then transform the second, and then add them together. And if you have a scalar multiple if you want to know how the scalar multiple of a vector is transformed, then you can actually just transform the vector and then scale the transformed vector, and you'll get the same thing. If both of these are true, then it is a linear transformation. So T of 0 is fixed. So that's a statement I already told you. And the linear combination of any vectors is also the transformation of a linear combination is the linear combination of the transformed vectors. It's just a combination of the scale multiple rule and the addition rule. And here it just shows that A is a matrix multiplication is a linear transformation, because using the algebraic properties of matrix transformations, you can distribute them out, so that's the same. And here you can factor out the C using our algebraic properties, and multiplying A times CU is the same as multiplying C times AU, so we're gold. Okay, let T be the transformation that takes R2 to R3 by this transformation. Is T linear? So there's two ways to do this. One, if we already have the theorem that if you can write this as a matrix multiplication, then it's linear. You can rewrite it as a matrix. Then you can try rewriting it as a matrix using the stuff we learned in class. That would be 2, 1, 0 times x plus 3 minus 1 minus 2 and so that's just 2, 3, 1, a minus 1, 0, a minus 2, xy. So we can rewrite that that T of xy is the same as just multiplying that matrix times xy. So T of xy is the same as some matrix times xy. So it's a linear transformation. Here below, we check the linearity criteria, where you can let u equal x1, y1, v equal x2, y2. So these are any 2 points, x1, y1, x2, y2. So then you can calculate uv, and then you can apply this matrix, plug in your u's and v's with your x1s, x2s, y1s, y2s, and everywhere where there was an x and y, you get these. You factor it out to the sums, and it simplifies to this, which is the same as T of u plus T of v. That's for the first part. What about the constant multiple times the value? So you can define u to be some xy coordinate. Why are we doing xy and not xyz? It's because we only have x's and y's here to work with. It just only transforms a point in the plane. So, xy, you can also write x1, y1 if you want, to show that it's just some arbitrary point. Let C be in the real numbers. Then C of u is just C times x, C times y. It's that matrix. And then apply the transformation. So everywhere there was an x and a y, you plug in Cx and Cy. And you can factor out the C, but then what you're left with is just the transformation of xy. That's exactly what we started with back here. See, this is what we have right there. And so you get C of txy, and that's the same as the transformation of just u. So transformation of cu is the same as c times the transformation of u, so it must be linear. That looks like Sina, but it actually is sense. But who am I to critique someone on their handwriting? What about this transformation? Well, that doesn't look like a linear thing with that squared, and this might cause us problems with the add 1. So the x squared is going to cause us problems when we, because it's not going to take a line to a line, and the plus 1 is going to cause us problems because it's going to shift us off the origin. So for those two reasons, those are the two intuitive reasons why this won't be linear. Down below, they do an example taking 1, 1, 1 and 2, 2, 2. So you can either think about this as 2 times x, or you can think about it as x plus x. And when you do the transformation, you don't get that the transformation of 2x is 2 times the transformation of x. So, sorry, I'll put that up there. It's a nice place for that to live. So here he was doing the addition one, but it does the same thing if you think about it as multiplication. Describe the linear transformations defined by these matrices. Well, this is the identity matrix. It's not going to do anything. This is going to keep your x's and y's the same, but your z's are going to become 0. And so this is going to project onto the xy plane. So this is going to stretch in the y. It's going to stretch a negative 2 times in the y direction. So it's going to flip it, reflect it across the across the x-axis, and then stretch it by a factor of 2. This is one I think we ended up doing in class, this was a rotation of some sort. So let's think about this. If I multiply it by x, y, I'm going to get a minus y and an x like this. So what does that mean? Let's say if I start with 1, 0, if I start with 1, 0, I end up with 0 and a minus 1. So it looks like I'm rotating that way. That might not be enough to know. I could have been reflecting along the, what about a reflection? If this is 2, 1, it looks more like 1, 2, actually. 1, 2. If this is 1, 2, then I end up at, the x is 1, y is 2. So my new x is a minus 2, and my new y is 1. So then I would do a minus 2 and 1. So it looks like I'm rotating counterclockwise. So I think I must have made a mistake on this first one, right? 1, 0 goes to 0, 1. That was my mistake. 1, 0. So that one, it went this way. This does a shear. So if I think of the point 1, 0, I end up with 1. I still end up at my x-coordinate is 1. My x-coordinate is 1, but my y-coordinate is 0. Look, I didn't go anywhere. Okay, that probably tells me my shear is going back and forth. I'm not shifting the right up and down, the left up and down. I'm going to shift the top one way or the other and the bottom the opposite way. So what about 0, 1? What about that? 1, 2, 0, 1. Then that means I go to 2, 1. So this point goes to 1. That point goes to this point. And if I started at 2, 0, then, or 0, 2, then I would end up at 4, 2. So that ends up at this point. So I'm pushing things this way. I'm shearing it that way. And I bet 0 and negative 1. Zero and negative 1. I should be shearing back this way. So I get a -2 and a -1. So that's what happens. -2, down 1. So that's the shearing. So to take this x, it would take this line and shear it to that line. And any line like this, it would shear it to something parallel to that. And this would take an x, y, z, and oops, it'll only take an x, y. So this takes an x, y, and what does it do? It gives me an x, y, 0. So it gives me the xy plane in R3. So that's what that does. So we have the standard basis, and I went through that fast because I'm hoping that you guys know the standard basis already. So let T be a transformation Rn to Rm, be a linear transformation, then there exists a unique matrix A such that T of x goes to A of x for all x in Rn. In fact, A is the m by n matrix whose jth column is the vector, the transformation of the jth standard basis vector, where Ej is the jth column of the identity matrix In. So what this theorem is going to help us do is it's going to give us a nice way to figure out what matrix will do the transformation that we're thinking about. Because all we have to do is start by looking at the 0, 1, 1, 0, or 1, 0, 0, 0, 1, 0, 1, 0, 0, 1. We just have to start looking at these standard basis vectors and look at where they go. And where they go becomes the new columns, or become the columns of our transformation matrix. So if we went back here, where did we do one of these things? Yeah, if we want, here, there's some space here, let me write this down. If I want a matrix to rotate to the left, or rotate 180 degrees, then to figure that out, I just have to figure out where does 1, 0 go, and where does 0, 1 go. If I rotate it around the origin 180 degrees. Well, 1, 0 goes to a -1, 0. right? One to the left goes that way, and 0, 1 goes to 0, 1 goes to 0 and a minus 1. So it would go from here and point down if I rotated it. Well, these are those are the columns of my transformation matrix. So I can find that I've done all the work I need to figure out what that transformation is. Is I just figure out where these basis vectors go to in the standard basis. Where does my x, my y, and my z unit vectors go, and then that tells me what the columns are. And so that's a really slick thing to know, because it can simplify a lot. We're not solving big systems of equations, figuring out A, B, C, and D. So it can help us. We still might be solving systems of equations, but this will help to simplify things for us. So this is the theorem that I mentioned in class. Every linear transformation is a matrix transformation. So find the standard matrix of the linear transformation, R3 to R4, defined by this. So using our theorem, so we can, we did talk in class about how to do this. We could break up 2, 3, 0, 1 times x minus 1, 5, 1, 2 times y minus 1, 0, 1, 4 times z. We could, and now we can rewrite those three columns in a single matrix times x, y, z, and we'd get this. Another way of doing this is you can use the theorem. We can just say, hey, where does 1, 0, 0 go? This is 1, 0, 0. If you plug in 1, 0, 0, so x is 0, all the others are, I'm sorry, x is 1, all the others are 0. You just get the matrix 2, 3, 0, 1, and lo and behold, that's the first column by the theorem that we just stated. How about 0, 1, 0? Where does that go? Well, that's just going to pull out the coefficients for the y. So you get a minus 1, 5, 1, 2. And what about 0, 0, 1? So that's just going to pull out the coefficients for the z's. You get that. So there's two different ways of thinking about it. Either putting them in columns and thinking about it as recognizing this as a matrix product. So that times x, y, z. Okay, or you can think about it as putting in the but the standard basis vectors, and that pulls out the coefficients also. So how about find the standard matrix of the linear transformation, which reflects vectors in the line y equals a negative x. So this is we did a very similar example, except we were rotating it around 180 degrees. But the trick is you just have to look at the standard basis vectors and figure out where they go, and then those where they go become your new columns. So I'm not going to take time to go through this one, okay? But you can come back, pause the video, and look through what they do. A linear transformation of a linear transformation ends up being just a matrix multiplication into another matrix. But order does matter, so this is the first transformation we do. And this would be the second transformation we do. So you don't necessarily get the same thing with AB and then BA. So this is the same. This is similar to functions, right? Where you can have composition of functions. We're going to do this transformation S and then the transformation T, sometimes written as T of S of X. So, and this is an example where you're thinking about two different transformations, and we use the strategy of just figuring out the matrix for one of the transformations, the first transformation, and then we figure out the matrix for the second transformation. And then to get the matrix that represents doing both of those in that order, you just multiply the matrices. So that was something I was hoping to get to in class, but we didn't get to it today. An invertible linear transformation, it's said to be invertible if there exists a function s such that you can take the transformed thing and get it back to x. So, and it won't surprise you that you can only do this if you have an invertible. If the transformation was originally done by a matrix that's an invertible matrix. So S is the inverse of T. If you, in general with transformations, but with linear transformations, it's just going to be A inverse. So, okay, I think that's it. That is it. Okay. Sorry, this is so long. I still know I was still rushing at the end to not make it too long. Thanks.